Hello, my name is Mark, and we did our project on the MPC for the optimal control of a vehicle launch. Our team consists of 5 mechanical engineering graduate students, and this is the outline that we will be following for today's presentation. We're going to be starting with a brief introduction of FSAE, describing our problem statement, our problem definitions, getting in depth into our MPC, and then also analyzing the results, and then discussing future implementations. To give some background on the competition, FSAE is a student design competition that is held by the Society of Automotive Engineers every year. It pits universities across the world against each other in various design, or static and dynamic events for the design of their race car. Some of the dynamic events include autocross, endurance, spit pad, and acceleration. The motivation for this paper primarily came from Berkeley Formula Racing's interest in improving their acceleration performance. So that is what the initial motivation for this project was.
So it's actually extremely hard for student drivers to achieve maximum acceleration for the whole duration of the straight line race. Therefore, we aim to create a controller that can take control of the car for the user during the launch to achieve this. So we aim to achieve maximum acceleration by matching our car's slip ratio to the optimal slip ratio, which gives us the highest longitudinal force and hence the highest acceleration. In order to do this, we need to create a controller that changes the car's input torque in order to control wheel slip based on the dynamics of the car. So what is wheel slip? Wheel slip happens when there is a mismatch between the wheel's velocity and the car's velocity. An example of this is when you're driving your car down the icy road and your wheel locks up. However, your car is still traveling down the road in a certain velocity. So in our case, we define slip as the ratio. This ratio is basically the difference between the wheel speed and the car velocity speed normalized by the car velocities. So if you look at the graph on the right below, you can see that the optimal slip ratio is around 0.1. And that corresponds to the highest traction force and the highest acceleration, which is what we're trying to get with this controller.
To simplify the problem, we're making a few assumptions. First of all, since we're only looking at the startup event of a race, we're neglecting any lateral loads that result from the vehicle cornering. Additionally, we're assuming that the vehicle is symmetrically loaded across the lateral direction. And also, when defining the relationship for load transfer of our vehicle, we're only considering the vehicle's weight and pitching, and thus no aerodynamic downforces are considered. We're also assuming road conditions to be constant throughout, and therefore the coefficient of friction is also constant. And finally, though not necessarily a realistic assumption, we're assuming that the max engine torque is constant regardless of RPM. For our model, we have one input variable, which is the combustion torque from the engine, as well as two state variables consisting of the vehicle velocity and engine RPM, which together can be used to calculate the amount of slip. These state variables also make sense since for the FSAE vehicle, with the sensors available on that vehicle, we're able to measure these as well. Our system dynamics consists of the Pacheco tire model, which relates to traction torque of our vehicle to the amount of slip the vehicle experiences based on the amount of loading that acts on these tires. Combined with the state evolution equations referenced from Professor Borelli's own traction control paper, we're able to formulate the system dynamics for our controller. These state evolution equations take into account not only the Pacheco model, but also other parameters such as engine damping, engine inertia, and gear ratio. And all in all, our controller will be optimizing over a nonlinear set of system dynamics.
So after defining our models completely, we went through to construct our CFTOC model. And since our reference slip is a scalar, our stage cost Q will also be a scalar. And we don't have any input costs because we don't want to penalize using larger inputs. And we also didn't include a terminal cost because we are trying to track the target slip throughout the entire course of simulation. So as a result, our constraints include the dynamics, the system models, and the states and input constraints. Initially, we tried to combine all the models into the dynamic equations, but the result became too nonlinear to solve by the sober IPOPT. So now let me dive more deeply into how we design our cost function. So we use a greedy search tuning method to sweep Q value to find the best model. And we evaluated our results by the time it takes to converge, the maximum velocity it achieved, and the stability and feasibility of our model. And we found out that the higher the Q is, the faster it converges to the target slip. However, the higher the Q it goes, the more infeasible steps we got in our controller. So in the end, we found out the best controller we have is when Q equals 9. So now after explaining how our MPC is formulated, Sebastian will explain you through the simulations with our MPC controller.
Thanks, Billy. To validate our dynamic system, we evaluated our models for the engine speed, vehicle acceleration, slip, and wheel traction for a given constant input torque. Analyzing the shown graphs, we determined that our state models show plausible results and thus could be used further for our CFTOC and MPC simulations. The graphs showing the evolution of our states throughout the task horizon are the results of a simulation on the MPC controller. Above, it is clearly visible how the engine speed initially reduces to the lower constraint bound at 4,000 RPMs to decrease slip before accelerating towards the upper bound. This engine behavior allows the vehicle to accelerate continuously as shown in the bottom graph. The goal of the MPC controller is to track the optimal slip value. The successful reference tracking can be seen on the bottom graph, which shows how the slip value converges towards the optimal slip value after a very short time. The top graph shows how the engine control unit will limit the engine torque to achieve the optimal slip, while the middle graph shows the resulting vehicle acceleration. To check the plausibility of our MPC model, we did a feasibility analysis. Given a wide array of initial states, we determined the feasibility of the MPC controller. As shown in the graph, a red dot resembles a feasible problem for given initial states. For our design cost function and constraints, we received a large set of feasible initial values, which helps us to determine the plausibility of our model. However, I would like to note that our feasibility analysis did give us a few small pockets of infeasible initial values.
For the future implementation of this controller, eventually onto an actual FSA racing car, there's a couple of steps that we do plan to pursue going forward. First of which being implementing gear switching in our MPC controller, so having the control be able to react to the driver changing gears and gear rate changing, implementing more realistic input torque constraints, making the MPC controller more robust to noises and more stable, and also eliminating the pockets of infeasibility that we currently have due to the software that we use. We also will need to eventually port our program over to Simulink, as our ECU only supports Simulink programs. And then finally, running and tuning our MPC controller on an actual vehicle and getting feedback on the actual dynamic model and our actual results from running the controller. Here are our references that we used in the research behind this project. We primarily took most of our models from Professor Borelli's paper, the first reference, and then we also took some parts of the dynamic model, primarily the Pacheco model, from the second reference. Thank you very much.